In this lesson we're going to look at the equation for the latent heat of fusion. Okay, so imagine that we've got some solid here. Okay, we don't need to know the name of it, but what we do know is that it's a pure substance. Okay, what we're going to do is we're going to supply heat to that solid, Q for heat, and so if we plot the temperature time curve for this process, we will see that its temperature rises and rises and rises until it just starts to melt. Okay, so there's a little bit of melting going on there as the solid is just starting to melt. So we've just got to here on our temperature time graph, and we reach this horizontal bit, and that's when the solid starts melting. And so from that point on, the latent heat is the heat that is absorbed by the solid in order to help it change from the solid state to the liquid state. So we can define the latent heat, and in this case it's the latent heat of fusion, because we're in the melting process, as the heat required to completely melt 1 kilogram of substance. Alright, so that's a simple expression which can be written as a simple formula. So for latent heat we use the symbol L, and because it's latent heat of fusion we put a little f there. So that's the latent heat of fusion is equal to the heat supplied to the solid during the melting process divided by the mass of the substance that is present. Okay, as the unit for heat is joules, it's a type of energy. Okay, we write joules, and then the unit for mass is in kilograms, so it's joules per kilogram. That is the symbol for latent heat of fusion. So before we have a look at a little practical problem, let's just remind ourselves about what's going on at the particle level. Okay, so we remember that in the solid structure the particles are vibrating around, but they're also held together by strong cohesive forces. And so when the solid starts to melt, this heat which is being supplied to the particles in the solid is helping them to overcome those strong cohesive forces and escape into the liquid state. Okay, so what's happening here is heat is being absorbed by the solid. In chemistry we call this an endothermic process. Okay, so melting is an endothermic process because heat is being absorbed by the solid to help the particles escape, overcome the strong cohesive forces within the solid to change into the liquid state. That's what's going on when melting occurs. And again, the heat required to do this is called the latent heat. Now, I just wanted to point out that exactly the same heat is involved in the reverse process. Okay, so when we have a liquid here which is cooling, then in order for it to transform into the solid state, this time it needs to release heat. So now the liquid is releasing heat. It needs to release heat in order to go back into the solid state. Okay, and it's exactly the same latent heat that's involved. Okay, all right, so we have latent heat is absorbed by the solid to help it melt, and latent heat is released by the liquid, the same latent heat, in order to help it to freeze. So we use the same equation for both processes, whether we're talking about melting a substance or whether we're talking about solidifying a substance. It's the same latent heat that is required. And so just going back to the chemistry again, in this case where the heat is released, okay, we have an exothermic process, whereas in the previous case where melting was occurring we have an endothermic process. So the absorption of latent heat to assist melting is an endothermic process, and the release of latent heat to assist solidification is an exothermic process. So let's just look at a simple problem. Supposing we've got 330 grams of ice cubes in a beaker and we want to know exactly how much heat is required to melt those ice cubes, assuming that they've just started to melt, so that we've just reached 0 degrees Celsius. Perhaps the ice cubes before started off at minus 10 degrees Celsius, and the temperature has just risen and they've just reached 0 degrees Celsius. Okay, so in that sense, we're sort of climbing up this this part of the curve here, and we've just reached the melting point for ice. Yep. And what we know is that there are 330 grams of ice. We want to know how much heat will be required to completely melt that ice. We want to know that. So the first thing we do is we write out our formula for the latent heat of fusion. LF equals the heat supplied, that's what we want to find, divided by the mass. Okay, so what we're looking for in this case is Q, the heat required, the latent heat required to melt that ice. So we rewrite that formula, Q equals LF, the latent heat fusion for ice, multiplied by the mass of ice present. Now this figure here, we'll find that from a reference manual, okay, or normally it would be supplied to you in if it's an exam question, and the value of LF actually is equal to 334 kilojoules. Okay, it's 1,000 kilojoules per kilogram. Okay, so the first thing we've got to be careful with here is, and this quite often happens in exam questions, is that the units are mixed deliberately to try and put you off. So we've got grams here and we've got kilograms here, so we've got to make this consistent. So we need to change this to kilograms, this figure, and to do that we divide by 1,000, which gives us 0.33 kilograms. And all we've got to do now is substitute these figures into our equation, which is equal to 334, so that's 334, K is 1,000, so we'll put 1,000 there for K, times 0.33, which is equal to 110,220 joules, or 110.22 kilojoules of heat are required to completely melt those 330 grams of ice cubes. Okay,